Mindsetters, welcome to today's Grade 10 Physical Sciences show. Today we have a special revision lesson on matter. We have selected highlights of lessons shown earlier in the term to help you revise Term 1's work. Please post all your questions and comments on our Facebook page on facebook.com/LearnExtra or on Twitter @LearnExtra so we can help you with your revision. Don't forget to download today's show notes on learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with our lesson.
So, let's just go through a bit of a summary about what we mean when we say the classification of matter, right? Well, firstly, it's important to notice that matter includes all substances that have mass, volume, and can exist in different states. So, everything around us that we can see is made up of matter. Okay, all substances would be matter. So that's our big general term. But from there, we can separate it in matter. We can group it into those substances that are mixtures and those substances that are pure compounds or pure substances. So from mixtures, we've got two different types here. Some mixtures are homogeneous mixtures. Well, let's just give ourselves some space. From mixtures, if I'm taking this route, some mixtures are homogeneous mixtures. Now, if homo means the same, we're looking at mixtures where you can't see the differences between the particles. So, some examples, maybe sugar and water. If you stirred some sugar into some water, that's a mixture because the sugar crystals will dissolve and spread out throughout the whole liquid. Okay, it's a mixture, and if you tasted that sugar water, it would taste sweet. So you can certainly notice it's got the properties of the two original substances. It's the water liquid, but it's also got that sweetness from the sugar. But you can't separate, or you can't see the different parts, right? Heterogeneous mixtures, on the other hand, hetero would refer to different. So heterogeneous mixtures would be where you can clearly distinguish the different layers or the different parts of that. So if I was to ask maybe a mixture like oil and water. Okay. There, if you shake it up, you could maybe see little tiny droplets of oil, but as you allow it to settle, the oil would all float to the top because it's got a lower density, and you could very easily distinguish, although it's a mixture and they're together, you could distinguish the different parts, the different layers. So we've had all matter is made up of, is going to be mixtures as well as pure substances. So mixtures, we've had the two types, homogeneous, can't see the different parts, whereas heterogeneous, you can see the individual parts of that mixture. Now, mixtures are very important because you can actually easily separate the different parts. They haven't chemically bonded, so it's pretty easy to, through some physical process, separate them out. So if I had iron filings with sulfur and I've mixed them together, right, you would see the yellow sulfur, you would see the grey iron filings. How could we separate them? Well, they still have their original properties. So the iron filings, we could take a magnet and move the magnet over. The iron filings would be attracted to the magnet because they have that property of magnetism, and so would definitely be able to be attracted to the magnet, and we could separate them out, right? So mixtures would be when two things have been mixed, or three or more have been mixed together, but they haven't chemically bonded. Then we have pure substances. Now, pure substances, we're going to separate further. So if I take these two arrows, and I'm just highlighting those two arrows down, pure substances would be when you've got something either that is an element, right, that is only one type of atom, right, or you can have pure substances that are compounds. So something like water, H2O, has got hydrogen atoms and oxygen atoms, but they've chemically bonded together to make a new pure substance that is water, right? These have chemically bonded together, which is why they're different from mixtures, right? But they are not made up of one type of atom. In comparison, elements are made up of only one type of atom. So whatever you do to them, if you try and break them down any further, you can't get anything other than that one type of atom. So if you've got iron, you've only got that iron. Okay? If you've got sodium, you've only got sodium. If you've got carbon, you've only got carbon. And even if you went down to an atomic level, you would still only have those carbon atoms. Right? So we've got elements and compounds, but these are all pure substances. Now if we talk through from elements, notice we can separate it further. And we will do this significantly as we look at the periodic table. Because all now these elements are listed on the periodic table. So metals will be found. There are metalloids, which is have got properties of nonmetals and properties of slightly of metals as well. So we categorize them together as metalloids. And then nonmetals, which would all be listed on the periodic table. And we'll do that in a few weeks' time. So going back to our big picture, we said all matter can be separated into pure substances or mixtures. Mixtures, we can think about homogeneous or heterogeneous. Pure substances could be elements, compounds, and elements could be metals, metalloids, or nonmetals. If we compare mixtures and compounds, because this is where students often struggle. If we compare mixtures and compounds, matter includes all substances that have mass, volume, and can exist in different states. The diagram below shows different types of matter. Well, we've done that diagram already, but I want us to consider this table where we're considering compounds and mixtures. Now, I've already given you a few examples of compounds being water or iron sulfide, or where these things have chemically joined together. So, it is a pure substance. It cannot be separated by physical means. So if I was to write here our example of water, H2O, that is now a new pure substance, and it has its own unique properties. In comparison, a mixture is an impure substance. It's not a pure substance. It's not got new properties. Compounds cannot be separated by physical means. I can't take a magnet and suddenly get the hydrogen parts to separate. I can't heat this and try and distill away, right? A pure substance is exactly that. It's a new pure substance. It can't be separated by physical means. In comparison, a mixture can be separated by physical means. Remember, I said they're magnetism, or I can pour through filter paper and filter out the larger particles, or the particles that have been that are not able to dissolve in the water. So those can be separated by physical means. A compound is always in a fixed ratio. Why? Well, it's because it's chemically bonded. So notice I've got H2O. There are 2 hydrogens for every oxygen. In comparison, a mixture is a random ratio of components. If I go back to my sugar and water example, I could put 1 spoon of sugar in and stir it up, or I could put 2 spoons of sugar in, and that would be more concentrated, but it's still a mixture in a random ratio, okay, of components. Or if we go over to the iron filings and the sulfur, I could put lots of sulfur down, or just a small amount of sulfur with those iron filings. So it's very much a random ratio. They haven't chemically joined together, and so I can separate them physically. Question 1. The table below gives the melting and boiling point of different substances. Now, when something melts, it changes from a solid, and it melts to form a liquid, right? When something boils, it goes from a liquid into a gaseous phase. Now, the melting point and the boiling point are temperature values. They're the temperature at which something will melt, the temperature at which something will boil, okay? And they are specific for different substances. So here we've got a whole table with melting and boiling points. And I think it would be very useful as you look at a table like this, and I find my students often struggle because what's going to happen is, as you look at this table, notice you're going to have some negative numbers. And it can be quite challenging because the questions that are coming are all about at what temperature is something a solid, Are you with me? So I would start, before going anywhere further, doing a number line. Okay? And my number line is going to be quite simple. It's just a rough sketch. It's not something that would be necessarily marked, but it's something that's going to help me to make sure I can answer these questions. So on my number line, and I've got this number line at the bottom here, I'm going to start with somewhere halfway, and that I'm going to put that as 0 degrees Celsius. And then I'm just going to go up in 50s, up and down. So that's going to be negative 50 degrees, negative 100 degrees, negative 150 degrees. Notice I'm working backwards so that these are the negative numbers, but it's going smaller and smaller and smaller. And then this side I've got 50 degrees Celsius, 100 degrees Celsius, 150 degrees Celsius. Now, of course, I could make that number line longer, but I think it will help just to get that skill, and maybe we can identify a few things here. So, water, what do we know? It melts at 0 degrees Celsius and it boils at 100. So I'm going to change, and let's go to blue. And I'm going to write here H2O. And it's going to be, that's where it melts. And that's where it boils. Now that might sound silly, but below that, do you agree that it's going to be a solid? Between those two, it's going to be a liquid. And after that, it's going to be a gas. Now, it might sound simple, but recognize that later on I might be asked some information. What is a solid at room temperature, or something along those lines? So this number line is going to help me. And I'm not necessarily going to do all of them, but hopefully, as I come across questions, I can slot them in. So I'm going to start with nitrogen. Nitrogen, and I'm not even off my, it's off my scale. So nitrogen down here at minus 210 is going to, N2 is going to melt. And at about there, it's going to boil at minus 195.8 degrees C. Carbon is going to melt way down there. So carbon is off my scale at 3,500. Ethanol. Now, ethanol, let's mark it off, is going to melt at 114 degrees Celsius. So it will melt here. Ethanol will melt. And where will it boil? At 78 degrees Celsius. So approximately there, and I'm going to write ethanol. It will boil. Okay? Now, all of those should be okay. Let's turn now to our questions and see what kind of questions we've got. But this number line is going to help me, and I will refer back to it. So let's turn to the next page and see what questions we've got. So I've got the same table there. Which substances will be liquids at room temperature? So I'm looking for anything that will be a liquid at room temperature. Now, room temperature is 25 degrees Celsius, and they tell us that in the question. So I can go back to my number line, very nice and easy, and I can say, okay, so I'm sitting approximately there at 25 degrees Celsius. Which will be liquids? Now, I go back, check the question. Have I got it? Yep, liquids at room temperature. And I need to consider this table. So immediately, can you see it's going to definitely be water, because water was a liquid between 0 and 100. So 25 degrees Celsius, water is definitely going to be a liquid. So on my list, I'm going to go down here and write water. Okay? Then I can go back across to my table. And let's see, we've done water. Water will be there. Nitrogen, it's already boiled way down below 25 degrees Celsius, so definitely it's going to be a gas. Carbon is still going to be a solid because it hasn't reached 3,500 degrees Celsius yet. Ethanol. Now let's have a look at this. We did list ethanol on our table, and we said ethanol will melt, which means here it's going to be a liquid, a liquid, a liquid, a liquid until there. So yes, at 25 degrees Celsius, ethanol is still a liquid. Are we happy with that? They're very, very important. And you recognize how a number line helps me to interpret what's happening in the table. Okay. So, answer the question. Let's go. We had water, we had ethanol. Next. What else? We've had that one will be, that one will be. Carbon dioxide. Well, carbon dioxide, I'm going to change color and let's put it on our table. On our number line, it was minus 78 degrees Celsius. So there, CO2. And let's move it slightly further down. And CO2 here will melt. And where will it boil? At minus 57 degrees Celsius. So it will boil there. Very low temperatures. Will it be a liquid at 25 degrees Celsius? No, it won't. So definitely not. Mercury, the next one. It melts at minus 38.83. So it's melting somewhere here. And I'm going to write down here, mercury melts. And where does it boil? It boils at 356. So also off my scale, mercury boils. Pentane, let's choose a different color, melts at minus 130, so somewhere there, pentane, and it boils at 36 degrees Celsius, so somewhere about here it boils, which means, it was pentane, which means at 25 degrees Celsius, where is it going to be? It's going to be a liquid. Are you seeing how this is going to work? So back to my answers. Let's write that in. Pentane. Next one. We had that one. Butane. Butane, seem to have run out of colors. Butane will melt at minus 140. So there's butane. And it boils at minus 1 degree Celsius. So approximately there, it boils. Now notice I've just done this for myself. It's just an explanation, and it's not particularly neat. But maybe different colors has helped you to recognize the different properties. Let's now use this number line to explain. We've got those answers. Did we list mercury? I think we've missed mercury out. Did we not? Mercury, we didn't tick, but definitely it will be. So, sorry, this way. Definitely mercury. At what temperature will pentane and butane both be solids? Now, this is going to be a range of temperatures. And I go to my number line and say, okay, when do they both melt? Or when do they melt? So, ethanol, sorry, it was a pentane. Pentane melts here at minus 130. Butane melts at minus 140. So anything below 140, they will still be solids, both of them. So, I keep going the wrong way. There we are. At what temperature will they both be solids? Below minus 140 degrees Celsius. Suggest reasons why mercury and ethanol are both used in thermometers to measure temperature. So once again, our number line is going to help me. Mercury, I had it over here. That was when mercury melts, so it's a liquid. Between there, all the way up to whatever it was at positive 300 and something, which is brilliant because it means it's going to be a liquid which will expand up the tube. Okay? Ethanol. Ethanol is a liquid from minus 114, and it's a liquid all the way to 78 degrees Celsius. So they've got a big range over which they will be able to measure the temperature. So we can have a comment here, the range of temperatures that will be commonly used to measure from room temperature at which they would be liquid. And you can go and list them. Mercury from, and we can go to our table and we can list that. Mercury minus 38 degrees Celsius. All the way through to 356, I think it was. 56.7. Ethanol, I'm just going to put it to the side here, was from minus 114 to 78.37, minus 114, all the way through to, 78. Let's just undo those. Minus 114, all the way through, degree C, to 78.37, I think it was, degrees Celsius. So notice that range of temperatures over which the substance will be a liquid and can expand up and down the tube. Next question. At what temperature does carbon dioxide exist as a liquid? Well, I'm going to go back to my table, and we had CO2 will melt and CO2 will boil there. So it's going to be from minus 78 degrees to minus 57 degrees. That's where it will be a liquid. At what temperature? And it was from minus 78 to minus 57. Anything through to minus 57 degrees Celsius. Anything between those two values. At which substance is the strongest? Now, you've got to go and look at your table and say, which one will the forces between those particles hold them together so much that they're not going to change phase? So, very easily. So it must be the one that has the highest temperature reading, or the highest boiling point reading, or the highest melting point reading. Okay? Both definitely would be carbon, and so on this table, carbon is the strongest. So carbon.
Alright, Mindsetters, I hope you guys are enjoying this revision session. Remember, if you are struggling and need help, please post your question on our Facebook page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, so don't go anywhere. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you on the page or on Twitter. Enough of the chat. Let's get back to the revision.
The next question of these improve your skills is basically to look at if I have some forces and I apply those forces to stretch a substance and then slowly remove that force, what's going to happen to the substance? So the first one, we have material X, and I apply the force, and notice the length increases. Then I start to reduce the force, and the length gets smaller, back to the way it was. The next question, material Y. I apply a force, and it gets to a point where it stretches. Even though I can keep adding a force, it doesn't get any longer. Okay, or it just continues with getting longer even as I go. That's what we call beyond its elastic limit. Okay. Now I remove the force, and what do you know about the length? Even though the force goes back to 0, the length doesn't. It's stretched and it's actually deformed. Material Z, I've applied a force, and actually this object has broken. Why do we say that? Well, we can definitely see the length has not gotten any longer, and I can't, if I reduce the force, the length is not happening there. Use the graphs to answer the following questions. Which material is the weakest? Well, it must be Z, because that snapped. Which material is brittle? Well, probably also Z. Why? Because it wasn't able to handle much stretching force. Okay, it just broke. It was brittle. Which material is the most elastic? Well, by most elastic, I'm meaning it can stretch and then it can reduce down in size as well. So that must be the first one I had, which is way back here, material Y. Material X, the first one. And which material is the most likely to be metallic? Well, you've probably seen metal springs. And you can stretch and stretch and stretch the spring. Maybe you've got a slinky or something like that. You can stretch it, but if it stretches beyond a certain point, it doesn't ever go back to its original shape. And that's what we're speaking about here. What's happening is that it's stretched, but it has deformed. So it's going to be Y, because it's metals can be stretched, but to a point, and then they're going to remain in that shape. Our summary. So, when we speak about the kinetic molecular theory, note it is a theory. It's a model that we want to use as we want to be able to explain what's happening in solids, liquids, and gases. And the theory basically says that all matter is made up of tiny particles. Okay? And those tiny particles could be atoms, if it's an element, or they could be ions. For example, sodium chloride would be in its ionic form, or they could be molecules. Some elements are molecules as well. Remember the diatomic ones, H2, Cl2, those kind of things. O2 would be molecules as well. But the basis of this is that all matter, if you went right down to the molecular level, would either be an atom, an ion, or a molecule. So basically all matter is made of tiny particles. Those particles, the second point, are always in motion, continuously moving. How will they move? Well, at high temperature, they're going to have lots of kinetic energy, so they will move faster. Okay? At higher temperature, the particles move faster. And heavier particles would have to move slower because they've got very big mass, so they're going to move more slowly. So think those through. All matter is made of tiny particles. Those particles are always in motion, constantly moving, and that motion depends on two things: the temperature at which they are, and secondly, the mass which they are made up of. And then the third point is that there are electrostatic forces of attraction between those particles, attraction and repulsion between the particles. So they're moving, and there are some forces between those. So kinetic molecular theory, basic idea is that all matter is made of particles. Those particles are moving, and there are forces between those particles. If we go down to the states of matter, we can explain those states of matter by thinking a lot around what's happening inside those particles, with those particles. So solids, well, again, made up of tiny particles. Have a look. I've got the solids there. The picture of kinetic molecular theory, I should say, of solids. Those solids are still in motion, but they vibrate around a fixed point. So all the particles are moving, but they're moving around a fixed point. And what that's going to mean is that they would have a definite shape and volume. They're not going to take up the whole space of the container, but rather they would be at the base of the container and fill up that space. As opposed to liquids, those particles are able to move and slide over one another randomly and would fill the base of a container. Okay? So in a liquid state, those particles are able to slide over one another. Last picture I have here is for the kinetic molecular theory for gases. And gases have lots of energy and are able to move randomly in all directions. So significant movement in comparison to liquids and solids. There are very limited forces between those gas particles. They've got lots of energy, so they will hit against all the different parts of the container and fill up the whole volume of the container. So very important that you can explain the states of matter in terms of the kinetic molecular theory and the basis for that theory. If we now speak about what happens during a phase change. So imagine I've got a Bunsen burner, and let's give it a little yellow flame, or a candle or something, and that Bunsen burner is providing heat. There's a little Bunsen burner, and so we are thinking about heating a substance. That is causing an increase in the internal energy of the substance. So overall, heating a substance is always going to be adding in energy, internal energy. But where does that energy go? Well, it can go into two forms. Either it can go into kinetic energy, or it can go into potential energy. Now, by kinetic energy, I'm speaking about the energy that a substance has, or a particle has, because it's moving. Okay, so particles that are moving really, really fast, they have high kinetic energy. Particles that are moving slowly are going to have low kinetic energy. So kinetic energy, the energy substances have because of their movement or due to their movement. Potential energy is the energy inside that they have because of their state. So I would be able to observe a temperature. Now, temperature has a distinct definition, and you need to understand this very well. Temperature is a measure of the average kinetic energy of the particles. So if I'm measuring, say, some boiling water, okay, or some water that's close to boiling point, I would measure that those particles, let's drop it down to room temperature. At room temperature, 25 degrees Celsius, the particles have maybe, say, a moderate amount of energy. But as I heat that, and it gets to maybe 50 degrees Celsius, those particles will be moving, on average, a lot faster. Now, we say average because not all the particles will necessarily be moving at exactly the same speed. But we're talking about the average kinetic energy, okay? So temperature is a measure of the average kinetic energy of the particles. And so if we could increase the kinetic energy, so if we say heating something up, if we increase EK, the kinetic energy, that will result in an increase in speed. Remember, we said kinetic energy is about how fast those particles are moving around, at which the particles move, and that will in turn increase the temperature. So increased EK is going to be an increase in temperature, always. What happens during a phase change is something quite different. During a phase change, energy is put into the substance, yes, but you will notice, and you can maybe even do a practical on this, maybe if you even just get some ice melting at home, and you put some ice in a jug, in a glass or in a jug, or even just a little plastic cup, and you can measure the temperature. And you've got to obviously keep stirring so that you distribute the heat evenly. But what you would notice is that while the ice is melting, sure, it's getting energy from the outside, but it's not changing its temperature. And that's something very, very interesting, because you would think, but surely ice is melting, it must be getting hotter. Well, it's certainly taking energy in, but its temperature is not changing. Instead, it is undergoing a phase change, which occurs as a result of the increase in potential energy. So no longer are we seeing an increase in kinetic energy, which it would then be observed as an increase in temperature. Rather, the energy that's taken in is going into a change in the potential energy of those particles. They gain enough energy to overcome the forces of attraction between them and break away from each other. So the temperature is going to stay the same. Temperature remains constant during a phase change. All the energy that's taken in goes into gaining potential energy so that those particles move and are able to overcome the forces of attraction. Now, this might be counterintuitive, but you need to think it through. Energy is going in, but where? It's going certainly into the internal energy, but where in the internal energy? Into changing its phase, so into potential energy, to allow those particles to move further away from one another. So if they were a solid like ice, they would be able to slide over one another into a liquid phase, and that's how you would observe melting. In comparison, once all of it has melted and you keep heating the substance, it will continuously then go into changing the temperature, and it will heat. The water now liquid water will start to heat up. So thinking this through, it's incredibly helpful to remember whether you're measuring temperature or whether you're measuring and observing a change in kinetic energy, or whether you're looking at a phase change. And in our next segment, we will be looking at and considering a cooling curve where you will actually see the temperature remains constant.
I'm sure you've seen the walk together photo on our page. Please post a caption and like the captions that you think are best. The 3 captions with the most likes will each win a pair of tummy tuckies. We'll post the winners on Friday, so get to liking and get all your friends to like too. Now it's time to take a break, so don't go away. We'll be right back. Welcome back from the break. I know you can't wait for the term to end and for the holidays to start. This year we bring you revision sessions from Term 1 from the 28th of March till the 6th of April. These will be repeats of all the Learn Extra live shows from Term 1. These programs will run from 9 a.m. in the morning till 7 p.m. at night. Go to our website learn.mindset.co.za for all the details. But for now, let's get back to the revision.
So, a graph below. Now, you have to be able to interpret graphs. Graphs are so important to science because, remember, maths and these kind of things is the language in which we often communicate. And so, to interpret the picture, the graph is so very, very important. The graph below indicates a cooling curve. Now, that's helpful because what it's saying is that we're starting at a high temperature and we're going to be cooling it down, okay? And now we are cooling it down. The temperature of a substance as it cools over time. So, have a look at the picture. We start off at approximately 120 degrees Celsius. Obviously, you need to read off a graph. And here I've got a sketch graph. But if you were given a test or an exam question, you would be able to read more distinctly off graphs with lines on the grid paper. It starts off at 120 degrees Celsius, and it cools right down to about 15 degrees Celsius down there. So over time it's cooling, but what I need you to recognize is that over the time it's going through some possible phase changes, and we can identify that because of those horizontal lines. Remember, during a phase change, the temperature remains constant. So here, definitely there's a phase change occurring as all of that substance changes phase, and so the temperature is remaining constant. Now I'm going to take that line away so we can hopefully come and answer some questions. Identify any phase changes occurring in the substance. So that's what they're going to be asking us to do. So I'm going to start some colors on this graph and write up what's happening. I'm going to start there and identify that is a gas. How do I know it's a gas? Well, I said to you it's undergoing at least 2 phase changes because there's a horizontal line which is an indication of a phase change. There's another one, and there's a third one, which we'll come to that a little later. So at the top here it's a gas, then it's changing phase, there it's a liquid, all a liquid. Here it's changing phase again, and so here it must all be solid. Now that's quite useful. Again, I'm now going to change color so we can identify. From B to C, it's needing to change from a gas into a liquid. So this is going from gas to liquid. Okay, and we need to name that, but we'll name it in a moment. Then from D to E, it's going here liquid to solid, and we need to identify what phase change that is as well. So from B to C, what phase changes that gas to liquid? We would say it's condensing. So this must be condensation. And I think I need to give myself some space and write down here. B to C, it is condensation. It is going from gas to a liquid. The next one, there's going from liquid to solid, and that would be freezing. So that was D to E on the graph. D, E, because recognize, they're saying identify phase changes. It would be freezing, and that is going from a liquid to a gas. What is the boiling point of the substance? Okay, now boiling point is the temperature at which something goes from a liquid to a gas, or vice versa, a gas to a liquid. It could also be called the condensation temperature, but we usually speak about the boiling temperature, the boiling point. It's a specific temperature at which that substance undergoes a phase change between liquid to gas or gas to liquid. So as we look at this graph, where it would change if I was heating this if I was reading from G, F backwards, it would change from a liquid into a gas from C to B. So that temperature, I'm going to need to read off the graph, and I'm going to take my little dotted line and line it up there. So let's see if we can undo that little line, and I'm going to try and make a little dotted line. You would dot that line across and read it's definitely 100 degrees Celsius. Now, water has a boiling point of 100 degrees Celsius, but we can't just assume that this thing is water. We'd have to read off quite a few more points before we could identify that. Identify the region on the graph when the substance is all a liquid. Okay, so where on this graph is it all a liquid? Well, from B to C, it changed from gas to liquid. From C to D, it should all then be a liquid, and that's how we would notice the temperature is dropping as this thing is cooling. But remember, it won't drop until all of that substance has changed. So it must be from C to D. So my answer here must be CD. It is all a liquid. Then what is the temperature of the room? Okay, we'll come to that in a moment. Have a quick look here. What is the temperature at which this thing freezes? At which this thing all becomes a solid? Well, again, I'm going to dot a line across. It's approximately maybe 45 degrees Celsius, 100 degrees Celsius, I'm not quite sure. it's 45, maybe 50 degrees Celsius. It's about halfway between 15 and 100, so it's approximately there. That's why I can tell it's definitely not water. What temperature would water freeze or solidify at? Surely at 0 degrees Celsius. So this is definitely not water. But now having a look at our graph, we've identified it was a gas, it's cooled and it's condensed, so it's become a liquid. The liquid has then cooled further and has become a solid through that phase change, and now it's all a solid. But what is happening at this point down there, F to G? Are there any further states that this thing could go into? No, there aren't. It's all already a solid. So why would it be leveling out? Well, think this through. Definitely, the temperature of the solid has dropped to a point, and then it has remained the same. So we must be able to say, well, surely the environment that this is in, it's cooling to its surroundings. It's not going to drop any lower than the temperature that the room is in. Okay, so from F to G would be the temperature at which the room is at. So what is the temperature of the room? Well, it must be at point F to point G, and we need to answer the question by reading off a temperature, and so I'm dotting that line across. Sorry, that wasn't a particularly straight line. Let's see if it will allow me to take it back. Taking that line right across, it should be 15 degrees Celsius. So that must be the temperature of the room, and I must answer here 15 degrees Celsius, and that is at the point FG. Okay, why? Because the solid temperature, that's all a solid, so it's not changing phase again, but it's cooling to its surroundings, the same temperature as the rest of the room. All right, we've got one more question for the Improve Your Skills. Stephen wants to know why his fingers often stick to the ice or to the ice tray when he takes ice out the freezer. And I'm sure that you've experienced this before. You go lift something out the freezer and your fingers start sticking to it. Why is that? Or even if you hold a block of ice, your fingers sometimes stick to it. Explain this to him using your knowledge of the kinetic molecular theory. So once again, we're wanting to talk about the kinetic molecular theory and the states of matter to explain why his fingers would stick to the ice as he removes it from the freezer. Well, this is an interesting question. You would recognize that your hands are relatively warm. Okay? Certainly relatively warm, much warmer than the ice as it comes out the freezer at maybe below 0 degrees Celsius. And so your hands are going to provide lots of energy directly to the surface of the ice and will melt the ice at that point. But because the rest of the ice is so cold, that energy will quickly be taken away from the surface around that block of ice. And so although the ice would have quickly melted, there will be moisture, it will immediately refreeze, and so your fingers stick because of the refreezing. So let's jot a few points down. Number one, we can say his hands are warmer. Obviously much warmer than the ice surrounding it. And so that would cause the ice to melt. Directly at that point where he's holding it, the ice will melt and will result in some moisture. Okay? When I say melt, it would go from a solid to a liquid. Remember, the question asked us to explain this in terms of the kinetic molecular theory and states of matter. So it's very helpful to make sure that you're linking in the states of matter. So the solid ice block starts to melt because his hands provide more energy for those particles to overcome the force of attraction and change state or change phase. So during that melting, there will be more moisture, as the energy his hands provide will allow them to overcome the force of attraction and change phase. But then that melted ice, the liquid, will change back into a solid. Why? Well, because very quickly, maybe we need to say here, very quickly that moisture will change back into a solid, and so will freeze, because of the high temperature difference. Okay, because his hands are so much warmer than the ice, the melted ice will quickly refreeze. Go back into the solid state. So it's going to be liquid goes back to the solid phase. The reason for that is that energy is very quickly taken to the other ice particles, and so it's going to very quickly refreeze. Now, maybe we should write that last point as energy is transferred or given away to the neighboring particles. Now, thinking this through, I think it's quite valuable to think about the fact that the temperature difference has resulted in a phase change, but because the temperature difference is so extreme, the rest of the ice is still so cold, it will take up a lot of that heat energy and will result in it refreezing. And that's why when you take ice out the freezer, or when this individual took ice out the freezer, it started to freeze against his hands and became a solid.
We've come to the end of our show. Thank you so much, Mindsetters, for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get your notes and to watch the videos from the term. Goodbye.